Hi, welcome back. So in this video, we are continuing our discussion about solving trigonometric equations. We're just introducing a new technique for solving them. Specifically, we're talking about how to solve trig equations using factoring. So you've probably learned factoring in a different math class, and you might not even realize that you know how to do it. And so we're going to just review what factoring is really quickly, because this type of problem we're doing with trig equations is going to use your factoring skills that you already have. So some examples might look like x squared minus x equals 0, where you're solving for x, or y squared plus 6y plus 9 equals 1, when you're solving for y. So both of these are factoring problems because we're going to use factoring to solve. So before I show you how to do these, my hope is that you've done this type of problem before, so why don't you take a second and try these on your own, try to solve for x and solve for y, and you'll use factoring here. So on this first example, we're going to factor out an x since both terms have an x in common. And when we do this, we get x times x minus 1, and that's still equal to 0. So we factor out the x times x minus 1. You can make sure you did that right by distributing the x back in. You'll get the x squared minus x. Then we solve this by setting each term equal to 0. So when two things are multiplied together and equal 0, it means that one of them has to be 0. So 0 times anything is 0. So this tells us that either x is 0 or x minus 1 is 0. And from here we solve. So the first one, x equals 0, is already done. The other one, we have to just move the 1 over to the other side. And so I'm getting x equals 1. So for this problem, my two solutions were x equals 0 and x equals 1. Okay, then for the second example, here we have something that isn't 0 on one side, so I'm actually going to move the 1 over to the left-hand side so that I have equal to 0. I like to use this property that two things multiplied together equaling 0 means one of them has to be 0, so I need that 0 on one side. When I do this, I get y squared plus 6y plus 8 equals 0, and now we are going to factor this. So these don't have anything in common. It's not like all of them have a y like we did in the first example, but instead here we're going to factor this into two pieces. There are different methods for doing this type of factoring. When I was in school, we learned FOIL, first, outside, inside, last, but I've seen new methods like using a diamond to orient the different numbers. Basically, whatever you need to do in order to do this is great. I personally don't really think about a technique in my brain. I've just done this enough that I can sort of do it. And so depending on where you're at in your math journey, this may be easier or harder for you. So here I'm going to factor this into two pieces that are each y plus or minus something and y plus or minus something. Since everything is positive, I'm going to do y plus for both. And I'm noticing that if I do 4 times 2, I'm getting 8, and 4 plus 2 equals 6. So my two factors are y plus 4 and y plus 2. If you need to confirm this for yourself, you can distribute out the parts. So the first terms give us the y squared, the outside and the inside terms give us that plus 6y, and then the last terms give us the 8. So now that we have these two factors multiplied together to get 0, we know that one of them needs to equal 0. So we can set up two equations to get two solutions. We have y plus 4 equals 0 and y plus 2 equals 0. With the y plus 4, we move the 4 to the other side, and we have y equals negative 4. With the y plus 2, we move the 2 to the other side, and we get y equals negative 2. And these would be my two solutions. You could always take your solutions and plug them into the original equation. You could substitute them in for the variable, and make sure that they work. So you could plug in negative 2 for y, and make sure that you're getting that the two sides are equal. Same for negative 4. So, okay. That's a little bit of review about factoring, and as long as you can do this type of problem, you're going to be totally able to do the trig equation version. If this is something you're still not that confident with, hopefully doing this type of trig equation can actually help you gain some confidence in this area. Let's try our first example. We're going to solve sine squared of theta equals 3 over 4 for all solutions theta in the interval from 0 to 2 pi. So for these examples, instead of finding all of the solutions using k as an integer and adding the period, we're just going to find the first solutions that are in the one swipe around of the unit circle. So we're going to just find the angles from 0 to 2 pi that work for this. So what makes this different from some of the other equations we've seen is that there's this squared. We have sine squared. So our method is going to be just to take the square root of both sides. So when we do this, we get that sine of theta equals the plus or minus square root of 3 over 4. Then we need to just do a little math here to figure out what the square root of 3 over 4 is. It should relate back to our unit circle. So if I look at that square root of 3 over 4, I can write it as the square root of 3 over the square root of 4, and then the square root of 4 is just 2. So I have square root of 3 over 2 as what I'm looking for. So from this, we have sine of theta equals plus or minus square root of 3 all over 2, and we're going to write two equations. So I use the plus version for one and the minus version for the other. So I'm really solving for sine of theta equals square root of 3 over 2, and sine of theta equals negative square root of 3 over 2. When I do this, I'm just going to be using a unit circle. You could use reference triangles if you want, or go through the process of using the inverse sign to find one solution with your calculator. I just like the unit circle because these are unit circle values. So for the positive version, I'm getting pi over 3 and 2 pi over 3. I'm just looking on my unit circle to find where the sine value is that positive square root of 3 over 2. And then for the negative version, I'm seeing that we have our answer as 4 pi over 3 and 5 pi over 3. That's where this sine value is a negative square root of 3 over 2 on my unit circle. And we're just looking for the solutions from 0 to 2 pi, and so this is it. I would write out all of my solutions as one list. I'd say theta equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And there we go. That's our answer. So, okay, I know this first one maybe didn't seem like factoring, and I guess it really isn't factoring, but let me show you how you can relate these types of problems back to the things you already know how to do. So when we start with this problem, this is really like solving x squared equals 3 over 4, but instead of x, we have sine of theta. So when you would have this problem, you would just solve for x by taking the plus or minus square root. And so you'd have x equals the plus or minus square root of 3 over 4, which then gives you the two equations. X equals square root of 3 all over 2, and x equals negative square root of 3 all over 2. And so you can see how this is related to what we did. So we did this by leaving sine in our equation, but you could really replace it with x and solve this problem first, and then think about x as being sine at the end. So I'll try to do this parallel method anytime I'm doing one of these problems to kind of show you how you can relate it back to the variables you know how to work with. All right, let's try another example. We're going to solve tangent squared of alpha plus tangent alpha equals 0 for all solutions alpha in the interval from 0 to 2 pi. So we're starting with this tangent squared of alpha plus tangent alpha equals 0, and right away it might help to think about the variable version of this, or like a parallel version. So this problem is like solving x squared plus x equals 0, where x is our tangent of alpha. So if you replace the x with tangent here, you can see how it is similar to the problem we started with. And so this looks like something we did at the beginning of the video. So here we can just factor out an x because both terms have an x in common, and we're getting that x times x plus 1 equals 0. Then this gives us two separate equations. Since we know that two terms multiplied together equals 0 means one of them has to be 0. So we get x equals 0 and x plus 1 equals 0, which that second equation gives us x equals negative 1. So this method here, I'm going through it fast because we're going to repeat the same thing but with our tangents. So if you ever are getting stuck on these problems, you can just relate it back to the other version with the variables, and that might help you out. So here with the tangents, I see that both terms on the left-hand side have a tangent in them, so I can factor out that common term. So instead now I have tangent of alpha times the quantity tangent of alpha plus 1. And if you need to confirm, you can multiply the tangent back in and distribute it through to make sure that you get what you started with. Then this gives us two equations. We have tangent of alpha equals 0 and tangent of alpha plus 1 equals 0. And now we're just basically doing two mini trig equations within this larger problem. And we can also see how this relates back to the parallel version of the problem we did. So when I isolate the tangents, I'm getting tangent of alpha equals 0 and tangent of alpha equals -1, which matches our two solutions of x equals 0 and x equals -1. So you can do what feels more comfortable to you. I like to keep the trig functions in just because this is sort of the new thing we're learning, but you can always go back to the parallel version of the problem using the variable in order to help you out. Okay, so now we just need to solve both of these equations for alpha. So starting with tangent of alpha equals 0, I know that tangent is 0 when sine is 0 because tangent is sine over cosine. So if you have sine over cosine equals to 0, this is true anytime sine is 0. So 0 divided by anything, as long as it's not 0, is 0. So this is true when sine is 0. And looking at my unit circle, I see that sine is 0 at 0 and pi. If you needed to check, you could plug in tangent of 0 or tangent of pi into your calculator and make sure it worked out. So those are my first two solutions. Now I'm going to use the tangent of alpha equals -1 to find some more solutions. So this one you could use reference triangles or the unit circle. I know that we get a -1 value anytime both the x and the y are the same. So this happens at the pi/4 angles, and I need the ones where we get a negative tangent. So I'm looking for either quadrant 2 or quadrant 4. And so my solutions in these quadrants are 3 pi/4 and 7 pi/4. So I'm kind of hoping at this point you know how to do that part of the problem, so I'm not talking about it too much. But of course, if you need a review on that, send me a message or leave me a comment and I can try to help out with that part. So together we have our 4 solutions in the interval from 0 to 2 pi, and we write them as one big list. So we say alpha is equal to 0, pi, 3 pi/4, or 7 pi/4. And there we go. Okay, so we've done 2 examples. The thing with this type of problem is that there are just always going to be so many different examples that you might encounter, and so I can't possibly show you all of them, but I do want to show you just one more type of this that you might see. But just know that you're going to encounter some examples that aren't exactly what we've talked about in these videos, and that's okay. Just try to trust that you have some background in this and that you can solve them. It might just take a couple extra minutes of looking at it and trying some things out to figure it out. So just remember, you're going to have to do a little bit of problem solving in some cases, and it might just not be an immediate procedure that you follow. So just try to trust that process and trust that you probably do know how to solve this. It just might take an extra minute or two. Okay, so for our last example in this video, let's solve cosine squared of beta minus 13 cosine of beta equals 14 for all solutions beta in the interval from 0 to 2 pi. So as before, we're just finding the solutions in the first sweep of the unit circle. So all right, we're starting with our equation here, and I'm actually going to just move the 14 over to the other side so that we have equals 0. We really like equals 0 because we can use that property where when we have a bunch of factors multiplied together equals 0, we know at least one of the factors needs to equal 0. So all right, I'm moving the 14 over, and now I have cosine squared of beta minus 13 cosine of beta minus 14 equals 0. Now let's look at the parallel version of this problem. So this is like solving x squared minus 13x minus 14 equals 0, where we replaced the cosine with an x. So we have x equals cosine of beta. Now this problem might not seem as intimidating. So here I'm assuming that we're going to be factoring into 2 pieces because I have the x squared and the x and the constant term. So I'm looking for 2 things that multiply to negative 14, but add to negative 13. And it seems like this is negative 14 and 1. So if I do x minus 14 and x plus 1 equals 0, this is getting me the equation I started with. And you can check, we do x squared plus x minus 14x, so that's our negative 13x, and then we get that minus 14. If you need to pause and take a second and try that out, make sure it makes sense to you, please go ahead. But okay, this will give us 2 solutions. So we have the x minus 14 equals 0, which gives us x equals 14, and then we have the x plus 1 equals 0, which gives us x equals a negative 1. And so these are our two solutions. So actually at this point, we could just jump back and write cosine of beta equals 14 and cosine of beta equals -1. But I want to show you these steps with the cosines written in just so you know what it looks like. So okay, we're going to repeat this factoring process, this time with cosines. So I'm going to have cosine of beta in the first part of each of these terms, and then I'm going to do my -14 and my +1 to have this work out. Now I just have my two equations. So I have cosine of beta -14 equals 0, and I have cosine of beta +1 equals 0. So I'm getting cosine of beta equals 14 and cosine of beta equals -1. And now I just need to solve both of these equations. So we were given a larger equation at the beginning, and now we have these two smaller equations that we need to solve as part of it. So cosine just goes between -1 and 1. That's as big as the values get. So if I have cosine equals 14, that's not going to have any solutions. So the cosine graph, for example, never goes up to 14 unless we transform it, which we haven't done here. And on the unit circle, you're going to see that the values are always between -1 and 1. They're never going to 14. So this has no solutions. That's okay. This part just didn't give us any answers. So looking at the unit circle, I see that cosine is -1 at pi. So my solution here is beta equals pi, and that's actually my only solution. So beta equals pi is the solution to this equation. Okay, so if you made it this far, I'm going to give you one tip. My suggestion is to just be really careful that you don't divide by any of your trig functions at any point. So we want to use factoring instead of dividing, because when you divide, you might accidentally be dividing by 0. So just keep that in mind as you're working through these. You want to be factoring and never dividing by a trig function, and you'll be good to go. All right, that's it for this one. Thanks so much for watching, and I will talk to you in the next one.